Hi students, welcome to YourPedia education and welcome back to the NPTEL questions module for electrical engineering branch. So in this session we are going to start in another question for electrical machines in electrical engineering branch. So we are starting a new question for electrical machines in electrical engineering subject. Okay, so what is the advantage of this NPTEL questions module is, which will give you a good amount of subject knowledge as well as good weightage for your preparation for your GATE and IIS and your PSUs also. Okay, so YourPedia is providing NPTEL book like this for electrical engineering, so and which will have different subject modules, separate sub modules, like different subjects will be there. So in this session we are solving the question in electrical machines subject. Okay, so the question number is this one. 17th is the next question what we are discussing. So if you take the 17th question into consideration, so it is again a DC shunt motor question. It is a DC shunt motor question, but here he has given some tabular data which consists of the magnetization curve at 1800 rpm. At 1800 rpm he has given the magnetization curve. So what is the meaning of magnetization curve means, which will give you the relation between field current variation versus your EA, that is back EMF or the EMF of the back EMF of the shunt motor. Now let's read the question and solve this question. What is the question he has given is a 27 HP 220 volts 1800 rpm DC shunt motor he has given, and armature resistance of 0.1 ohms he has mentioned, and the field resistance he has given as 176 ohms. This will be ohms. Okay, and assume ET equal the back EMF is equal to terminal voltage at no load, because at no load you don't have any load, means you don't have any current flow in the circuit, so which will be equating the back EMF as well as your terminal voltage. So this is the tabular data which gives the relation between IF and EA or EB. So now the motor is used to drive a load which requires a constant power of 16 kilowatt. So this motor is driving a load which requires a constant power of 16 kilowatts, and the motor is connected to 220 volts DC supply. What is the question he is asking, or what is the thing we need to calculate in this question is determine the range possible with a field rheostat of 180 ohms. So here we need to absorb the question in such a way that speed range he is asking. First, speed range. So there is a speed variation, lower limit and upper limit he is asking in between the value, and where a field rheostat is connected with 180 ohms and it is varying. Because of the variation of field rheostat, how the speed will change. So as this is a field flux control method of speed control, we can say this is a field flux method of speed control. So where you will get the speed will be above rated speed. Speed will be above rated speed. So what is the value, which value it will be, you can select from this one, means from which value the speed will vary. From which value speed will vary. So the rated no load speed will be 1800 rpm, and from that the speed must be more than that value. The speed must be more than that value. Yes or not? So or if you take the no load speed, so the speed versus your torque variation, if you take no load speed will be very less in value, very less in value, that is that will be little lesser than 1800, and the speed, because of the presence of a field rheostat, which will be more than the rated speed. So we'll have two types of speed control. One is armature resistance control and the second one is field flux control. So armature resistance control or armature voltage control will give you the speed less than the rated speed variation, and this field rheostat control or field flux control will give you the speed which will be more than the rated speed. Now let's solve this question. By using the basic data. So first let me draw the circuit or electrical equivalent representation of the DC motor. So this is the DC shunt motor. So here you have a shunt field winding like this, and this is connected to what type of load? Some load it is connected, and how much amount of power it is absorbing? 16 kilowatt. 16 kilowatt. So this motor is connected to some external load which requires a constant power of 16 kilowatts. Okay, so this is the motoring load I am talking about. Don't think that it is a generator. So here this is a load. This is the load which requires a constant power of 16 kilowatt. So this is the motor load which is connected on the DC motor, I can say. So now based on this data, because what is the terminal voltage of your motor he has given? He has mentioned it as 220 volts. And so what happens to the back EMF, as well as how much amount of load current it will flow through the circuit, how much amount of load current it will carry. So if you check with the load, so this is the terminal voltage. Let me take this as a current IA. So then what happens to the load power? Load power which is equal to V into IA, or so usually under no load condition this V and IA both are same, but under loaded condition this V can be replaced with EB. So this is the mechanical power which will be delivered to the motor, So how you will write the EB value? So which can be rewritten as, EB can be rewritten as V minus IA RA, so into IA. So from this one, what is EB value? Under no load condition, what is the EB value we have? Or EBIA product he has given, that is 16 kilowatt. So 16,000 is equal to V is 220 and IA minus IA square into RA. So bring all the IA terms onto the other side. IA square into what is RA value he has given? It is given as 0.1 plus 2 minus 220 IA plus 16,000 equal to 0. If you solve this equation, because it is a simple second order equation, so which will give you the current ratings as two values of currents will get. So what are those values we will get is 2124 amperes is one value. So another value will get as 75.3 amperes. Among these 2124 can be neglected, so the current value will get it as 75.3 amperes. Now as we know the current, so we can calculate the back EMF VB, which is equal to V minus IA RA. So from this one we can calculate the back EMF, which will be equal to 220 minus 75.3 into 0.1, so which will give you the 21 how much value? 212.47 volts. So now, so what is the next thing he has given? He has connected a field rheostat, and that field rheostat is varying from minimum value to maximum value. During that variation, what is the amount of speed variation? That is minimum speed and maximum speed, how much maximum speed it can attain and how much minimum speed it can reach. So both values we need to calculate, so that will give you the range in between minimum speed to maximum speed. So first let me take the first condition. What is the condition is, if field rheostat is at minimum position, minimum or 0 position. So if the field rheostat is at 0 position, what happens to the field current? So field resistance is, field current is equal to the terminal voltage by the field resistance plus external field resistance. What is the terminal voltage? It is 220 volts. divided by what is the field resistance value? It is 176 ohms plus what is the external field resistance we added here? That external field resistance is equal to how much? As it is at a minimum position, we can say that this is 0. So once it is 0, so how much amount of field current you will get is 1.25 amperes. So if you observe the field magnetization curve, so for 1.25, is there any voltage is there? Yes, there is a voltage. So for 1.25, the back EMF voltage is obtained as 214. So for 1.25 field current, for IF1 which is equal to 1.25 amperes at 1800 rpm, the back EMF voltage BEB which is equal to 214 volts, So now we got the voltage, Now based on this EB, so what is the relation between EB, flux and speed? So EB is equal to pi z NP by 60A. So this can be rewritten as back EMF is directly proportional to pi into omega. So where omega is equal to angular speed, that is 2 pi n by 60. This is the omega. So this can be rewritten as back EMF is equal to some k1 into phi, omega is the speed. So from this one, so now calculate the k1 into pi function, because we know the back EMF voltage of 214 and we know the speed is at 1800 rpm. So what is the voltage we have? 214 divided by omega is 1800 rpm, but we need to convert it into radians per minute. It is there, it should be converted into different value, 2 pi nt by 60. So from that one, so 60 by 2 pi or 2 pi by 60, sorry. So 2 pi by 60, because this is the speed, 2 pi n by 60, right? So you need to do this. So if you solve this one, how much amount of value will get it as? 1.135. So now you know the k1 into pi. So as we know the value of current, so and we got the back EMF, we know the constant k1 into pi. So if I take the ratio of k1 into EB by k1 pi, because k1 pi into omega will give you the EB, so but the actual EB is this one and k1 pi is the constant for IF equal to 1.25 amperes, so that I'll take the ratio of EB with respect to this k1 pi, which will give you the new speed value. Now let's calculate that value. So what is the new speed? N is equal to EB1 or EB by k1 into phi. What is EB? It is 212 point, how much is we got? 212.47 divided with k1 pi is how much? 1.135. So this will be the speed in omega we will get. So let me rewrite this expression as omega. But I want speed. So if I want speed means you need to just take the into 60 by 2 pi. So 2 pi n by 60 will give you the omega. We have omega, we need to convert that into rpm. Okay, so this will give you the speed value. How much value, speed value it will give you is 1787.6 rpm. 1787.6 rpm. Similarly, let's move to the field. If field is at maximum position, so if field is at maximum position, so the field current is equal to 214 is the rated voltage divided by 180 ohms is the resistance of the field circuit, and so if this is this one, R external field, which will be equal to 180. So and the rated field winding resistance is 176, which will give you the 0.618 amperes. So now from the table again, so what is the value of this one? What is the value of EB at 0.618 amperes? At 0.618 amperes, if you observe, it will be 0.625 is 160. So it will be 0.618 means it will be little lesser than 160. Let us take it as 158 or 157 something. So based on this value, for field current of 0.618 amperes at 1800 RPM, so the back EMF will be how much? It will be 158, I'll take, and 158 volts. So if you have 158 volts, let me calculate the K1 pi, which is equal to 158 by 1800 RPM into 2 pi by 60. So this will give you the how much amount of value? 0.84. So from this one, what is the omega, which will be equal to, so how much amount of current will flow through, what is the back EMF EB value we got? We got EB value as 212.4 with respect to 0.84 into 60 by 2 pi, into 60 by 2 pi. So which will give you the speed value will be 2415.4 RPM. 4 RPM. So now if you observe this question into consideration, what is the speed range we got is 1788 to 2416. So 1788 to 2416 or 2450. So answer will be C. Now I'll give you the simple analysis of this question. So without solving all these things, you can pick the right answer, nearest to right answer we can pick. So how it will be, let me tell you. If you observe this question, so what type of speed control it is? It is field flux control. Now let me take a new slide. So what type of speed control it is given? Field flux control. Field flux control, speed control. So if we take field flux speed control, the rate speed should be greater than rated speed. So what is the rated speed we have? 1800 RPM. So the answer will be more than 1800 RPM. So the maximum speed will be more than 1800 RPM. What about the minimum speed? It should be very nearer to 1800, but under no load condition it is rotating at 1800. But actually DC shunt motor will not rotate exactly at the rated speed. It will operate at very nearer to rated speed like this. So you might have seen the speed versus your current or torque characteristics. So this is the rated speed if you observe. So this will be the actual speed, which will be actual speed. So there is a small difference between actual speed and the rated speed like this. So did you observe this one? So this is the variation of speed from no load. This will be the rated speed. This will be the rated speed or no load speed. This is the full load speed we call. But even under no load condition also it will not rotate exactly at the rated speed. So it will operate very nearer to or less than rated speed. So this lower limit, upper limit will be greater than 1800. Lower limit will be so less than 1800, but which is nearer to 1800. So based on this analysis part, so which option will be more satisfied? 1600, 1642. It will never be the correct answers. Next, what was the next one? 1820, which is more than 1800. So this will not be the correct answer. The one and only answer you can pick is 1788 to 2450. So this is how you need to analyze the subject. This is how we need to analyze the subject. Once you are perfect in basics or fundamentals, these kind of analysis you will get by your own. Okay, so this is how you need to solve this question. Thank you, all the best.